Yes, can you people see the screen and hear me clearly?
Yes, sir.
Okay, good morning everyone. So we shall start with today's topic, first being expectation maximization. Okay, so here I will tell you everything in only one word. Okay, then the next 15 minutes we will talk about it. Okay, so what this particularly topic conveys is it's all about probability. Okay, it's all about probability, guessing. Guessing what? Guessing the missing values, okay, which is not there in the data set. Now, having said that, first we will see, okay, given a particular sequence such as coin, okay, and if I tell you, and I'm giving you two coins, okay, I'm going to give you two coins, okay, and Raj is standing here. Raj should get, okay, what is the probability that five coin B is being tossed one three times and coin A is being tossed two times? What is the probability of getting head and what is the probability of getting tail of coin B and coin A? Okay, so then we can make a guess and we'll see a particular formula and we'll get some values. The next what we will be seeing is, now the rat should guess, he doesn't even know which coin is being going to be tossed out of those two coins. Okay, that is coin B or coin A. So the problem becomes more complex. Even he doesn't even know what happens. The coin, which coin is being to come, which coin is going to toss first. Now again he has to make a guess, and that guess should be the probability of the missing value. That guess what you're going to be, okay, make should be fair enough or good enough. The result should be producing a good output. Okay, so based on these things, we will proceed. Okay, it was first introduced in 1977. Okay, by lots of mathematical derivation. So the problem given of a data set is data is incomplete. Incomplete means what? Missing values. You have some record with the values and some record with not no values. Now what is the goal? Is to assume the set of data that comes from the underlying distribution from some model. We need to guess. Okay, and that guess should be maximum likelihood parameter of that model. Okay, so the missing data is there. We need to fill the missing data. For that, we are going to guess it, and that guess should be maximum likelihood. ML means maximum likelihood. ML, maximum likelihood. Given a set of incomplete observed data, assume that the observed data comes from a specific model. Okay, this observed data, whatever is there, okay, incomplete data, observed data comes from a specific model. Based on this, we formulate some parameters for that model. So based on these parameters which is being formed, okay, we use this particular parameters to make the guess, the missing data, and try to fill it up. That is called as an expectation. From the missing data and the observed data, so you have now already you have some data. Now you have the missing data also, which you have filled it up with this particular expectation step. Now you have the observed data which you already have. We combine together to find the parameters model. Iterate the step 2 and 3 till you get the right value, of the missing data, till it gets converged. Okay, so each step cluster based on the current data, that is the observed data. M step generate the best theory to get the clustered data. So where are the things this EM algorithm is used? Actually, it is used in multiple places, and it actually forms the foundation of ML itself. So it uses in clustering, artificial vision, biological areas, natural language processing. So these are the places where you can apply this concept of expectation maximization. Okay, so you have the observed data structure. Now you make the guess of the unknown parameters and you form the parameter. So then you combine make the E step, and then you combine the E step with the observe step. Okay, M steps. Okay, and then you repeat the step 2 and 3. Okay, step 2 and 3 till it gets converged. Okay, what does it do? Expectation maximization is an approach for performing maximum likelihood in the presence of latent variable, means missing variables. In the presence of missing variables, it does first by estimating the values for the missing variables, then optimizing the model, then repeating the expectation and maximization step until convergence. Okay, fine. So now let's get it done. Okay, so we need to form the complete data. Z is the complete data. How are you going to form the complete data? By whatever the values you have, that is whatever the values which is already given to you, observed data X, and the hidden data. Okay, that is what we are going to find. Okay, so X is the observed data and Y is the hidden data, which is the missing data. Okay, to get the complete data, and this complete data should have a good a good prediction model, a good clustering model, a good whatever the output model, but it should have the complete data and it should be a quality. Kindly note that all the machine learning engineers who are there in the industry, for them coding is just only 2 or 3 months for any given project, or 6 months or 8 months. To gather the data, they take 1 year or 2 years or 3 years, irrespective of whatever the project it is. Once they analyze and they build the data set, now it's plug and play only for them, for the leaders of the machine learning engineers. Okay, so now to get the complete data, okay, observed data is there. Okay, and when the client comes, he get only he gives the bits and pieces. The other parts of, let it be cancer prediction, or let it be liver prediction, or let it be any prediction, or let it be any model, or let it be in any restaurant, or let it be in hotel, or let it be in healthcare, or let it be in any industry, in whichever a production, automobile, or whatever it is, they give incomplete data at times only, most of the times. So with that incomplete data, they find the missing data, and then they try to build the model Z. So many people uses EM model, expectation maximization model. It's an iterative method to perform what? Maximum likelihood. Starts with an initial estimate. It starts with an initial value, and then you go ahead with it, and then you refine the current estimate, trying to increase the likelihood of the observed data. Okay. Okay, now students, X is the observed data. Head tail sequence. Hidden data, coin ID. Initially, students, we will give you, we will see a problem with the coin ID. Then we will hide it. And then we will see how to increase the probability. So first we are going to give both everything. Okay, there are no missing values at all. Initially, we will see X and Y, both are given. Okay, and there are no missing data, so the data is complete. So the target, okay, first if the coin ID is not given, we don't, as I told you, right, in the first case, Raj knows which coin A and coin B Rajiv is going to toss, and based on that he is going to produce a head or a tail. In the second case, the Raj doesn't know which coin Samuel is going to toss, so the coin ID sequences we are not going to give. Okay, so in the second case, which you don't know, the target is to figure out the probability of the heads of the two coins. Maximum likelihood estimates can be directly calculated from the result. Then we will make sure, then we are going to talk about, okay, the ID sequence itself is not known. Okay, now let's begin, students. Okay, the first case, everything is given now. Okay, now Raj knows which coin is going to come. So coin 1 is there, coin 2 is there. Two coins. Theta 1 be the probability of getting hit of coin 1. Theta 2 be the probability of getting hit with coin 2. Find the values of theta 1 and theta 2 by tossing the coin for multiple times. Here we will keep the multiple times as 10 times. Okay, we are going to toss the coin 10 times. Okay, toss for the first 5 times, choosing any coin randomly. Select one coin has to toss for 10 times. Okay, so now students, we are going to bring in a sequence. B is tossed, coin B is tossed, then A is tossed, then coin A is tossed, then coin B is tossed, then coin A is tossed. And how many times it is tossed? 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So coin B after tossing 10 times, coin B after tossing 10 times, we get 5 head and 5 tails. And you see this is a sequence. 5 head and 5 tails. Coin A after tossing 10 times, we get 9 heads and 1 tail. Then coin A after tossing the coin, we get 8 heads and 2 tails. Okay, coin B after tossing the coin 10 times, we get 6 heads, 4 heads and 6 tails. And coin A after tossing the coin, we get 7 heads and 3 tails. Okay, done. Okay, done. So theta 1, number of heads with coin 1 divided by total number of flips using coin 1. Theta 2 is calculated, the probability we are calculating basically. Number of heads of coin 2, because we are bothered about only about what? Head. See, what is the probability of getting head? We are not bothered about tail. Okay, probability of getting head. So theta 2 after causing the coin, okay, 5 times. That is after causing the coin 10 times. Number of heads with coin 2 by the total number of flips. Okay, by the total number of flips using coin 2. Okay, done. So number of hits. Okay, so now what are we going to do is, so if we see, okay, the number of hits, so for coin A, 9 plus 8 plus 7, okay, 7 plus 8, okay, 7 plus 8 plus 9, which is 24, which is 24. So 24 divided by total number of times, total number of times is, okay, 24, 25, 26, 27, 28, 29, 30. 30 is 0.8, is 0.8 for coin A, for coin A, maximum number of heads. Okay, for heads. Now, if you see this one, if you see this one, 5 plus 4, 9, 9 heads, 9 heads, and what is it given here? 6 plus 5, 11. So 9 plus 11 is 20. So 0.5. Okay, so now it becomes very easy. So the probability of coin A getting head is 0.8, and the probability of coin B getting the head is, okay, 0.45. Okay, 80% and 45%. Fine. Okay, this students, this is the maximum likelihood. This is the maximum likelihood. Okay, this is the maximum likelihood. Okay, now we know which coin is tossed. B, A, B, A. We had the label heads. This is the label head. This is the label head. Now, okay, now we don't know, okay, which coin is tossed now. Whether the B coin is tossed or A coin is tossed. We don't know. We don't know the label of the coin AB. So we cannot calculate the maximum likelihood. So we cannot. Here we know we are able to calculate the maximum likelihood. Okay. Here we know we are able to calculate the maximum. Here we don't know the label. Here we don't know the label. Here we don't know the label. In such case, when we don't know which coin is coming first, whether B, A, B, A, we don't know the sequence of the coin label. In that case, we use expectation maximization algorithm. Expectation maximization to calculate the maximum likelihood. If we don't know the identity of the coin. Okay, so now what does the algorithm says? Okay, start with what? Start with initial prediction or probability, a random guess. So random guess, can you see? Start with initial estimation of theta values. I am starting with initial estimation of theta 1, coin A, coin B, 0.6 and 0.5. Then we will try to maximize this. So here we use binomial distribution to find the likelihood. Now what is the binomial distribution? Theta of k equal to 1 minus of theta of n minus k. So where n is given by the number of flips, okay, 10 times or whatever may be the number of flips. Okay, students, n. Okay, and k is the n is the number of flips and k is the number of heads or tails from the number of flips taken. Okay, likelihood for the first coin flip. Okay, likelihood for the first coin flip. Okay, so 5 head and 5 tails. Okay, now we don't know see sequence. Some coin is coming. Okay, so let it be whatever it might be. Okay, we don't know the sequence. So the sequence. Okay, can we please understand? This is not given, but this is given now. Please understand. Only the coin sequence is not given. So when the coin sequence is not given, we don't know what is the probability of coin A and coin B. So now, but this is given. So okay, so we have the coin which is being tossed is 5 heads and 5 tails. Okay, so probability of first coin. Okay, so K is 5. 1 minus of 0.6. Okay, by total number of flips is 10 minus 5. You get this value. Okay, then likelihood of B. Likelihood of B. Likelihood of B. So 5 again. Okay, 5 tails. So 1 minus of 0.5. Okay, so I get this one. Okay, heads and tails. So LA. Okay, this is LA divided by LA plus LB. I get this value. The same way, LB divided by LA plus LB. I get this value for the first coin flip. For the first coin flip. Okay, now in the similar fashion, we find the probabilities of all the coin flips. So this one for coin A. Can you see? I have done it for coin A. So 0.45 and 0.55. Okay, 0.45 and 0.55. So we have got 0.45 and 0.55. So for the probability of A and probability of B. Okay, now for coin A, head and tail. For coin B, head and tail. So now what am I going to do? If you look at this, okay, so for probability of head is probability of A into number of heads. The probability of tail is probability of B into number of tails. That is say for example, if I'm going to do this one. Okay, say for example, so 0.08, can you see 0.08 into coin A heads. Coin A heads is 9. Coin A is 9. If I do this one, 9. Okay, and one tail, and one tail, and one tail. Can you see? And one tail. So 0.80 into 9 equal to 7.2. Okay, and 0.80 into 1 into 1. Okay, into 1. 0.80 into 1. Okay, which is zero point 0.8. Which is zero point 0.8. Okay, then point again 9. This is 9, right? 9. Okay, not 0.9, 9. Okay, so 9 into 0.0 probability of B. And you see, I'm filling up the missing data here. I'm filling up the missing data here. I'm filling up the missing data here. Okay, so 0.18. Okay, then what I do? Then 0.20 into 1. 0.020. I fill this. Like that I do for everything, students. I do for everything. I do for everything. So this value I have calculated, right? This value I have calculated. Like that you will be calculating for all the values. The same way, this value is computed, okay, based on the whatever the values of 5 into 5 into 0.45, then 5 into 0.45, then 5 into 0.55, then 0.5 into 0.55. I get this one. Then 9 into 0.8, then 9 into, then 1 into 0.8, then 9 into 0.20, then 1 into 0.20. Then what do I do? Then 8. Okay, then 8 into 0.73, then 1 into what is that? 2, 2, right? 8 and 2, right? 8 and 2, then 2 into 0.73. Okay, then 8 into 0.27, then 2 into 0.27, then what? Okay, 6, 4 and 6, then 4 into 0.35, 4 into 0.65, and 6 into 0.35, then 6 into 0.5. I get this. So I get this. So I calculate this entire table and fill up the missing values. Can you see? Fill up the missing values. I start with my probability and then I filled it up with the missing values. Then after filling up the missing values for coin A and coin B. So for coin A and coin B, what I do the summation. Summation of head and tails. Summation of head and tails. What is the summation of it? Summation of this one. and summation of this one, summation of this one, summation of this one. So summation of coin A head, summation of coin A tail, theta 1. So summation of coin A, summation of coin A. So this theta 1 and theta 2 will be sent to the next iterations. Will be sent to the next iteration. So the process will continue time and again, time and again, time and again. Okay, then after 10 iterations, I get theta 1 as 0.80 and theta 2 as 0.50. Okay, 0.80 and 0.50. Okay, then you see after 10 iterations, after 10 iterations, 0.80 and something. Okay, related. Now I'm predicting. Okay, now predicting with the sequence and predicting without the sequence. Clear, students? Hello? Is it clear to everybody? Hello? Okay, can you see, students? Now after you do for 10 iterations or might be 20 iterations or whatever may be 15 iterations. So say for example after 10 iterations it is 0.80 and 0.520. Now you see here that is this with the sequence, what am I getting? 0.8 and 0.45. But after 10 iterations without the sequence, see I'm getting still 0.8 whatever it is and 0.52. So this is how you calculate the maximum likelihood. Able to get it? Hello? Hello students? How many of you
Yes,
understood? Can you
sir.
raise your hands? Quickly. This is called as expectation maximization. Okay, very good, students, very good. Okay, so now the next topic. That's all, students. That's all. So the next, can you please put your hands down? The next topic we'll enter into the module 6, and the first topic is principal component analysis. Principal component analysis. Okay. Now, students, in principal component analysis, when you have multiple features, that is multiple columns are there, age, gender, okay, blood pressure, okay, then for example x1, x2, x3, x4, and it goes on, and it goes here something like this. That is the point. What I am trying to tell you here is, if you have one to say for example 100 columns, it is 100 dimensions. 100 dimensions are there. 100 dimensions are there. If there are multiple dimensions, okay, usually in machine learning, we call it as curse. Why we call it as curses? As the number of dimensions increases, there is a possibility that accuracy gets decreases. Because more and more dimensions gets added up. Okay, fine, accuracy is one part, okay, fine, but there is a slight chances, okay, that the accuracy also get decreases as the number of dimension increases. Okay, now to do that, we convert these dimensions into lower dimensions, such that the accuracy is not getting affected. The accuracy, the decreasement of the accuracy is not getting affected. And very important point, the information loss should be very minimal. Okay, kindly please understand these few words what I am trying to say. As it means that I am trying to remove a column. If I'm trying to remove a column from the machine learning, that column might have some important information. If I have information column is removed, okay, if the information column is removed, okay, then it might have again have an impact on the accuracy. Kindly Kindly please understand. Keeping the column also will increase the accuracy, decrease the accuracy, or removing the column might also decrease the accuracy. So while removing, I should be very careful that which particular column, that is which particular feature of the data set to be removed. Such that, example, if there are 100 columns, if I remove one particular column, that is 100 dimensions are converted to 99 dimensions, and that one particular column which I am removing should carry very less information, such that it does not impact the accuracy. That is what I am going to do, or I am going to show you, or we are going to learn. Okay, now let's see, students, how are we going to do this entire process? Now let's consider, students. Now let's consider. Understood, students, what I told you just now? Understood what I told you just now? Here, when I'm telling you to put your hands down, please put your hands down. Okay, it means that you are not available there. And if you are not available, I'm going to mark you as absent. Why I'm putting you to hands up and hands down means, it means that you are listening to me. That is what it means. Very good. Okay. So, understood, students? You can just talk to me. Understood? What did I just say now? Understood?
Yes, sir.
Okay, because if you understood the first few lines only, students, you will be able to understand what exactly is happening. Why is sir telling all these things? What is the reason where I can apply in my project if I go further? If I face some kind of a similarity, let it be in the industry when I move, or let it be in your projects, what you're going to do. Kindly please understand. Okay, the moment you leave machine learning only, your actual machine learning project starts, where you have learned multiple things and you can try to incorporate it while learning. Okay, you are going to learn every day. Okay, and if I tell you to do also, okay, you will not be able to put everything together. Why? You have not learned everything. You have learned only decision tree. With the help of a decision tree, you cannot do anything. So every day you are learning. So after learning everything, once you leave out only, your actual project starts when you put your hands into machine learning. So that is why I'm telling you. So again, I'm telling you, when you have multiple dimensions, 1 2 3 4 5 6 7 8, say for example 1,000 dimensions, if the number of dimension increases, the accuracy decreases. So what am I trying to do? I am going to reduce the dimensions. Say for example, just to make you understand, if I'm going to remove 2 dimensions and say for example 998 dimensions, but if these 2 dimension carries very much lots of information, again please understand the accuracy will still decrease. Why? These two features what you have removed might carry more amount of information, contribute more to the amount of data set. So adding is also a problem, removing is also a problem. So now we are going for removing of the dimensions. So while removing, we are going to apply principal component analysis, such that while you are going to remove these 2 columns, while you are going to remove these features, very less amount of information is lost. If the very less amount of information is lost, the accuracy is still maintained high. We go for principal component analysis. So principal component analysis is a dimensionality reduction technique. Okay, now let's consider what are we going to achieve and how are you going to remove. So converting, let's consider, students, we have a data, 2 features, f1 and f2, and I have plotted my points over here, okay, in 2D representation. Now if I want to convert 2D into 1D plane, can I draw a line something like this and map all the features onto the line, and map all the features onto the line, and map all the features onto the line? Yes. Now since I have mapped all the features onto the line, can all the points will be something like this, which lie on one plane? This is my 1D. Okay, this is my converting from 2D to 1D. Okay, so projection of all the 2D data points, I have mapped it. So, and my new features are this one. Okay, this is my 1D. This is called as my first principal component analysis 1. Now, to map these points, I can draw n number of lines and try to map it. Yes or no? This is one way of drawing the line and mapping it. Okay, students, for these particular points. Now, the second PCA line, I can draw something orthogonally like this. And now I can map all these points to this one. Can you see? I am mapping all the points to this one. I am mapping all the points to this one. So this is called my second principal component analysis 2. Principal component PCA2. We can call it PC1, PC2. Now you tell me, mapping the information from here to here was easier, or mapping the information from to this PC2 line was easier? Which one of the information data will be lost more? Whether was it PCA1 or PCA2 line? PCA2 line. Come on, students, tell me. Please tell me. PCA2 line was more. Hello? Please tell me fast, students, so that I can proceed. I don't have time. Which information
PC1
loss
also.
was more? Loss was more.
Sir,
PC2.
PC2.
PCA2, sir.
Very good, student. So it makes a basic common sense. It means that you are able to understand. Excellent. Hats off. So PC2, PCA2. Okay, students. Now I can draw any number of lines. I can draw any number of PCA lines according to my dimensions. If there are 100 dimensions, I can draw 160 to 70 depending upon, or 90, 95. Okay, and I can draw any number of lines, but the particular line which can be very less amount of information which is lost, I will make that as PCA1. Then the next line I will choose it as the next priority will be given to PCA2, then the next priority will be given to PCA3, and it goes on and on and on. So that particular feature will be selected first. Okay, and it goes on. So as I told you, I've just shown you. So mapping, this is my PCA1, principal component 1. So PCA2 should be orthogonal, a straight line. Okay, now comparing PCA1 and PCA2, okay, lots of variance is lost. So PCA2 has, as you told, very good, lots of information is lost. So when selecting PCA, the less amount of line, that is the least amount of information is lost. So mapping from here to here to this line, or mapping from here to here to this line. Okay, this line information is lost more. So we take this line. Okay, so we will calculate PCA1 component 1. We will calculate PCA component 2 analysis line. Then we will see which one is losing more high, have a lot of variance. Accordingly, we will take decisions. So in case if you have 500 features, I will create as many lines, okay, n lines, but make sure it should be less than the number of features, less than, not equal to, less than. It should be less than the number of features. If you have 500 lines, I can create 400 lines or 450 lines or whatever may be the lines. It should not be greater than or equal to 500. Okay. Now if you see this one, so see, can we see these are all so many orthogonal lines I can draw. This. I can draw, keeping on drawing so many orthogonal lines. But which is the best line? I've just shown you. And you see, these are all so many orthogonal. Can you see which point of the data where the minimum amount of the information is lost? See. So this particular point, can you see? Oh my God, I cannot pause it actually. If you see a point which comes when this line comes somewhere over here, okay, where all the points are converging together at the minimum point where the information is lost. Just draw and see. See when it comes here. Can you see, students? Hello? Hello? Can you see?
Yes, sir.
Okay, so it's a dimensionality reduction method. Okay, it is used to take out some features from the large data set such that, okay, the features which we are going to take out should be selected very carefully such that very less amount of the information is being lost. Okay, and the features which we are going to contain or we are going to select carry forward should contain more amount of information. Should contain larger the value, it means that more amount of information. Smaller the value, it means that less amount of information. Okay, it's taking. Okay, so reducing the number of variables. Okay, everything whatever I have just told you, I have written. Okay, reduce to number of variables in the data set while preserving as much as information as possible. So now students, just let me give you an example. Okay, you will have a various idea. So I have 1 2 3 array 4 5 6. Okay, I think so. Here it is. Okay, 1 2 3 4 5 6. Okay, 1 2 3. Okay, 2 4 6. Then 4 8. I think so. Something somewhere I've gone wrong. Okay, 1 second. Somewhere 4 6 8 or 1 2. Actually, something have gone wrong. Something have merged. Let me check the overlapping which has happened. Let me proceed. I just want to convey one point over here. For that one, I have chosen this example. Okay, now students, I have 1 2 3. Okay, then 2 4 6. Okay, then 4 8 12. Sorry. Okay, I got it. Okay, it's one number. Okay, I just got confused. It's 12. Okay, it's 12. Then it's 15. Okay, and it's 18. Correct. Now students, 1 2 3. If I multiply it by 1, if I multiply it by 1, I'm getting 1 2 3. 2 4 6. Okay, if I multiply it by 2. Okay, okay, or divide it by 2. Sorry. Okay, if I divide it by 2, again I get 1 2 3. Right, 4 8 12. If I divide it by the particular number 4, I get again 1 2 3. Right, 3 6 9. If I divide it by 3, okay, again I get 1 2 3. 5 10 15. Again if I divide it by 5, okay, I get 1 2 3. So 6 12 18. Again if I divide it by 6, I get 1 2 3. Now students, now please understand, 1 2 3, 2 4 6, 4 8 12, 3 6 9, 5 10 15, and 6 12 18. If I store as it is, if I store as it is, so if each occupies 6 bytes, okay, so 3 6 are 18, so totally 18. 18 bytes are required. Okay, 18 bytes are required. Now if I adopt this particular method of storing, can you see, of storing, okay, 3 bytes, that is only 9 bytes are stored, that is 1 2 3 is stored, 1 2 3 is stored, and then 1 2 4 3 5 6 is stored. 1 2 4 3 5 6 is stored. So 6 plus 3 is 9, so 9 bytes total itself is required. 9 bytes. So here total to store the same data I require 18 bytes. Here I just apply the PCA toy on this particular example, I store only 9 bytes, so 50 percentage savings. 50 percentage savings. And remember, I am maintaining the information also. I am maintaining the information also. Okay, I'm maintaining the information also as it is. Now the same concept I'm going to apply in PCA. I'm going to apply in PCA. Okay, so students, I use eigenvalues, eigenvectors, and covariance. Okay, the concept what I'm going to use is eigenvalues, eigenvectors, and covariance to do the dimensionality reduction such that I'm going to take out the features. Okay, and if I take out the features, the most information should not be lost. Okay, fine. Students, so I have I have one using eigenvalues, eigenvectors, and the covariance. Okay, so now I have 10 values. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have this 10 values over here. Okay, I have this 10 values over here. I have this 10 values over here. Step number one, students, take out the mean. Step number one, take out the means. Step number two, covariance. The covariance factor. Since it is 2 cross, this is a dynamic formula. If you have 3 cross 3, then it will be Cx. Okay, then the Cx1, Cx2, Cx3, accordingly it will vary. Okay, XYZ. Okay, XYZ, accordingly it will vary. If it's a 3 cross 3 matrix. Okay, 1 second. What happened? Okay, so now it's a 2 cross 2 matrix. So for the 2 cross 2 matrix, how I have is, so I have XX over here, I have YY over here, I have XY over here, and I have YX over here. Now I want to find the covariance. How I want to find the further. So the covariance of this particular formula, x and y and x are same, because if you multiply, reverse and multiply 3 into 4 and 4 into 3, it's going to produce the same number. So always the covariance, whatever the x and y and x is the same. So if you find out any one, you can put the number over here also. Same. So the covariance of x comma y is xi comma x bar yi comma y bar into n minus 1. Okay. So, okay, the covariance of y comma x is yi comma y bar and xi comma x bar, okay, divided by n minus 1. Now, covariance of x comma x is xi by rs x bar, xi minus of x bar, multiplying with by own, and n minus 1. Okay, and the same way the covariance of yi minus y bar by n. So, you have the formula. Okay, now how do I find out? So, for this to plug in the values, I need to find out. Okay, let's start with covariance of x minus of x bar. So, for two values I have done. For two values I have done. So x is 2.5. Okay, the second value is 0.5. Y is, okay, so now x minus x bar. So 2.5 minus 1.81, which is this. Then 0.5 minus of 1.81, which is 1.31. So multiply x minus, so 0.69 into 0.69 minus 1.31 into minus 1. I get this. The same way I do it for y minus of y bar. Okay, 2.4 into minus 1.91, 0.7 minus of 1.9. So when I do this, y minus y bar, so 0.49, okay, the whole squared, 1.21 the whole squared, I get this. So you do this for all the 10 values, I get 5.490. Okay, divided by n minus 1, n is 10, so 10 minus 1 is 9. Okay, the same way what you do is you do it for all these values. I get 6.49. So 6.49 divided by n minus 1 is 9. So I get this. Okay, now after doing that, I do it for the covariance of x comma y. So x value is given, y value is given. X and x bar value you have already found out. Plug in all the values over here. Y minus y bar you have already found out. Plug in all the y values over here. So I get x minus y. Multiply x bar this and this. X minus x bar y by now. I get this one. Divide by n minus 1. Divide by n minus 1. Divide by n minus 1. 9. So this is the sum. When you add up, I get this value. So query. So now it's x and y x both are the same. Okay. So now I formulate the covariance matrix. And you see, I have formulated my covariance matrix. I formulated my covariance matrix based on the values. Okay. Now step number 2. Okay, to find the eigenvalues. So the formula is covariance minus of lambda into identity. So the covariance matrix we have find out lambda into identity. So when you plug in the values and when you do the math, okay, so we get, I have done, okay, I have done this, most of the steps I have done individually. I get lambda squared minus of 1.33 lambda plus 0.623. So use the calculator to get the lambda 1 and lambda 2 values. I get lambda 1 and lambda 2. So you should put in descending order. You should put in descending order. Okay, so lambda 1 is the eigenvalues, okay, and lambda 2. So put it in the descending order. So lambda 1 carries most of the, here itself you can calculate. I will tell you in the end. Okay, so lambda 2. So after calculating the eigenvalues, for each eigenvalue, you will be calculating the eigenvector. You will be calculating the eigenvector. So for the eigenvector, formula is this. Okay, covariance into eigenvector equal to lambda into eigenvector. So covariance, okay, will be helpful till you finish. So we have calculated the covariance. The eigenvector is x1 x2. So since there are two x1 x2, x1 y1 and x1 y1. Okay, so when I plug in the values, I get this equation, these two equations. Okay, so 0.x5 minus x1 and plus 0.5 minus y1 equal to 3 and 0. I get these two. So you can use any equation to get the value of x1 and y1. So I will get something like this. I will get something like this. I'll get something like this. And you see, this is y1. Okay, y1 is missing. So I will get something like this. Now, if I put, because y1 values can be to find the particular perfect eigenvector values, y1 can be varied with so many numbers. But to come to a standardized form to find the final exact value, just put y1 as 1. Just put y1 as 1. So if I put y1 as 1, my x1 is this one. So 0.91. Get the final eigenvectors for lambda 1. For lambda 1. Okay, for lambda 1. Okay, so what will I do? So just take the square root of this and square root of this. Sorry, square of this, not square root of this, square of this. Okay, after taking the square of this, I take a square root. Then I get 1.3610. Then I divide 0.91 divided by 1.3610, which I get 0.6678, and 1 divided by 3.61, which is 7.35. The same thing I will do for eigenvalue lambda 2. Eigenvalue lambda 2. So when I do for eigenvalue lambda 2, okay, I get this particular equation. Okay, and when I take this over here, I get x2 equal to this. Very simple. You just do nothing, no rocket science at all. Okay, basic 6th, 7th math. Okay, and I have solved step by step also. Okay, so x2 equal to minus 1.8052. Okay, now the same thing happens. To find the value of there can be multiple variations of y2. So to get the perfect eigenvector value, okay, for x2, okay, y2. Okay, this is y2. Okay, so what I do, I just put y2 as 1. So when I put y2 as 1, x1 1.084 and 1. Okay, so y2 can take any value. So to find the exact eigenvalue, I took y2 as 1. Okay, fine. So now when I put y2 as 1, so I take the square of this, I get this value. I take the square of this, add them. Okay, take the square root, I get this, divide this by this, I get this value, and divide this by this. So now I have two eigenvalues for eigenvectors. Two eigenvectors. Out of these two, okay, lambda 1 carries more amount of information than lambda 2. How come? How come? I just do the simple math. 1.2840 divided by 1.2840 plus 0.49. I get 96% of the data. This carries. Can you see? Vector 1. 2 equal to 0.490 divided by 1.20 plus 480, 4% of the data. So this is PC1, principal component 1, and this is principal component analysis 2. So now what I do is I can remove this particular feature vector, and I can use this particular vector for my further computations. Okay, for my further computations. So this is my matrix what I have got. Okay, this is my matrix what I have put. Discard the eigenvector v2, which is one of lesser significance. So which is lesser significance? So this carries 96% amount of the data, and this carries 4% amount of the data. Okay, so I can discard this one. Okay, I can discard this vector v2, and I can take v1 carried forward. Okay, so the dimensionality reduction I have reduced from 2 to 1. So discarding the eigenvector v2 will reduce the dimensionality by 1 and will consequently cause a loss of information in the final data. Or the loss of information for final, but v2, was carrying only 4% of the information compared to v1 still carry 96% of the information carried by v1. So it will not affect that much accuracy. It will not affect that much accuracy. Is it very clear to you, everybody? Is it very clear to everyone? How many of you have understood? Raise your hands, please.